Okay, first of all, I want to thank you, the organizers, for letting me speak here. Okay, so we had very good talks today and really amazing talks. So for my talk, we are tired and let me start with something very simple. So semi-groups. Okay, and the simplest mathematical object. So you have a set. Let's make any set. I don't know, A, and then you have an operation on that. So it's closed on the operation, closed under this operation, and associativity, and maybe let's put one inside A. Okay. So the thing about semigroup is that we cannot do just taking semigroups. We cannot just study semigroups like that. We need to have structure on the set and a particular operation so that we can do something meaningful. Okay, but to the extent this is very nice, very easy to work with, has very good. So we can do very concrete calculations in this setting. So now so let's find some applications in commutative algebra. So what do I mean by applications? I mean that, so does any property of semigroups corresponds to some property of some particular rings? Okay. So let's look at one of them. So let's take one of the easiest semigroup. Let's take S to be a semigroup inside the set of non-negative integers. Okay. So I will be putting this 0 inside this. So just please don't mind. Okay. So now, if I construct, let K be a field. Let K be a field. Okay. If I construct this ring, which is generated by maybe P of S belongs to this semigroup. Yes, let me construct this string. I think it's not the best way to write this. I think this is the best way to write this. S belongs to S. P of S, maybe K years, I don't know. Okay. So this, what happened is that, let me give you the result. So Kunz, in 1970, he showed that this ring K of S is Gorenstein if and only if this S has this following properties. The first property that S has is that its complement inside the natural numbers is finite. Okay. The second property is this: S is irreducible. What do I mean by that? It does not live in something big, in the usual sense. Something big, I mean something big that also has a finite complement. Okay. And the third property is that S is something so-called, let me put the easy word. The maximum in the complement of S is odd. So if you're, yes, constant, yeah. I think so. So the definition of irreducible is that if there exists like T1, T2 inside N, such that T1, Ti inside this is also finite, then and T1 set T2 is S, then Ti is S for some I. Yeah. So you see that this very easy looking set, very easy to compute, very easy to do. So if just having this if it has these three properties, then the ring you construct from it is Gorenstein. Okay. Now you can ask something. So this also carries forward if you start looking at semigroups. This kind of correspondence that you have, this application, you start looking for semigroups S, maybe inside n to the R, maybe it's in the tuples of R. So there's a theorem by Goto, Suzuki, Watanabe in 75. They said if my H is inside an R is a finitely is an affine semigroup. Let me just is finitely generated semigroup. Okay. And then L is the subgroup generated in Z of R. Okay. And there exists F1 to Fn Li over the rational numbers such that H lives inside the positive cone of that. Then you can say that this ring K of H, this is in n polynomials. Okay. This ring K of H is Cohen-Macaulay if and only if you have this property for W inside L, if WFI H and W plus F J in H or some 1 I J N, then implies. Okay. So the point of this is that, like, if you jump in more variables, then Cohen-Macaulay can be abstractly just checked by the structure of the semigroup. There's some property of if the semigroup satisfies this property, then the ring satisfies Cohen-Macaulay. There's also a result. There's also a characterization for R being Gorenstein, like if and only if property. I would not write it because of time. And there's some recent work by Ito, Masuka, Nomata, Watanabe in 2024. They have done this for like almost Gorenstein, almost Gorenstein, simplicial semigroup rings. Okay. So the takeaway is that you can construct some semigroups, and then the rings you make out of that, just the property of the semigroups can tell you can give you very interesting properties of the ring. Okay. So this was the motivation, like motivation why we should care about semigroups by themselves. Okay. So now what happened is that so all this semigroup theory that we discussed now were semigroups in MD. Okay. So what further generalization we can make from NR? Anyone? Oh, okay, yeah, Z. We can do this is Z, same thing, right? Like you can make Z, but then it is isomorphic to Z, like kind of like anything inside you can isomorphic. So what are the generalization you can do? So my advisor came up with this idea. So let's study semigroups. Semigroups inside linear groups. Okay, very fancy term. And is it too much to ask? So, but let's break down this question. So every linear algebraic group can be written as a unipotent part, a semi-direct product with a reductive part. Okay. Linear algebraic groups are just subgroups, in GLN, which are also variety. They can be written as a unipotent semi-direct or reductive part. Okay. This is some linear algebraic group terms. So what we did is that we make an analogous theory in study semigroups in the unipotent part. Unipotent part. So what does this gives us? So let me make things more concrete. So let me write the set U of n, which is n. This is a subset of n by n matrices with ones in the diagonal, 0 down here, and all these entries such that all these entries are inside n. Okay? Unipotent, upper triangular unipotent matrices with entries in non-negative integers. So we will study submonoids of this ring. So we study S that lives inside U of n. And the operation we give is the product operation. So this group is this monoid is closed under multiplication matrix multiplication operation. More generally, what we can do is that more generally, what we can do is that we can take a finitely generated monoid inside U of n and take semigroups inside this M. This is the general version. And now, so you can ask me now, how can I go back to the easy version? So I have come to here. Can I go from here to here? I say, yes, you can go from here to here. How? If you just take the matrix like 1, 1 in the diagonal, and you take this M to be, just the first row is non-zero, and everything else is 0. So this is commutative. If you multiply two matrices having first row non-zero, everything 0 unipotent, then this is isomorphic to n of b minus 1. So you can so generalizing semigroups into this context is the generalized version of n to the r, and it looks more nice, more sophisticated. Okay, now so we have defined this thing. So the question is it useful, or can we do something with it? And then for that, first we need to make some foundations, foundation. So this started with this one question. There was this Wilf conjecture for complement finite submonoids, semigroups in N. Okay. Is anyone aware of the Wilf conjecture? and we just write it. It's an easy peasy conjecture, but it's not solved. Like very easy to state. So I think let me show you. Where is that? Okay, somewhere here, right? Yes, yes. So if S is a subset in N, so I mean semigroup, complement finite semigroup, and then if you let C is equals to max, C is the maximum number in the complement plus 1. If you let E is the minimum, the cardinality of the minimum generating set, cardinality of min generating set, and you write your this N to be maybe those S belongs to S such that S less than max. Let me give you an example what this says. This says that if my S is something like, give me something 3, 5, 7, 8, 9, everything onwards. I cannot 3, 5, 6, 7, 8, everything onwards. So my C would be 4 is not here, so 5C is 5. My E would be, this is generated by 3, 5, 7. So E is maybe 3. And my N, everything less than 5, 0 and 3. There's 0 here. So 2. So the Wilf conjecture says that you always have C less than equals to E times N. Wilf conjecture always says that. It's not proven. It's, So after doing this construction, but we were able to introduce this so-called unipotent Wilf conjecture. So I will not write down everything. So we define this invariance, and we have some conjecture that kind of looks like the same. This dimension times C less than equals to EM. And I won't go into details, but we can do that. Okay, that's one good thing. We have done something. We literally not did something anything interesting, but now come the next paper, we did something interesting. The first paper was just to see does things work in this context or no. In the next paper, we introduced the theory of relative ideals. Relative ideals. So for any semigroup, for any semigroup S, you can say something is an ideal. This lives inside Z. So it must satisfy two properties. The first property is that if S plus I, this must lives inside I. And the second property is that there exists big N such that N plus I lives inside S. So this is the notion of ideal in semigroup theory. So we were able to generalize this theory in our setting. Sorry for me being too vague, but we were able to generalize this theory of real ideals in semigroups inside finitely generated monoids of U of M. Okay, and what we can do is that from here, we have this one result. My professor and me has irreducible ideals, let me write irreducible unipotent monoids are either symmetric or or pseudosymmetric. This was the first very interesting result that we got. And after that, our current work is that we can define these things like blow up sequences and some ARF sequences, ARF closures, and something like reduction number for this setting, and then we can have some more results in this. So this is our current work, what we are doing. And a question that I would like to propose to this audience is that, so the motivation I just gave you. So there was an algebra, and then you say some properties go here and there. So can you create an algebra from this cumulative thing? Yes, you can. So let me give you a small algebra. So suppose you take 3 by 3 matrices. So you take U3. So these are like 3 by 3 matrices. 1, 1, 1, and 3, 3, 3 by 3. Okay. And then you just take formal combinations of U3. Or in general, you take any monoid inside U3, and you take a semigroup inside this monoid, and you take this as formal combination. So the multiplication is in this algebra is just matrix multiplication, and addition is just formal. Okay, formal addition. So this is let's just put K here. Non-commutative. Non-commutative. And the thing is that so there is notion of Gorensteins and everything, this same thing in this algebra. You can make some note or CM. So can you get the similar correspondence between properties of this, which are well defined, which are like well defined properties, and well analog properties of the base case? Can you have similar correspondence into this ring? So this is an open, like I'm working on this now. So yeah, so this is it. Good. Is any questions? It was just stated we prove for some particular cases, and we gave a justification that this bound achieves its maximum also, and this is very hard to go above that. And then we also compared it with some, like last year someone did some similar kind of conjecture for ND, and then we compared with that. And this thing is new, so there's this generalization to unipotent matrices has never been done before. So this name, we came up with these names. So yeah. Conjecture then is it's like if you could show this. Yes. Yeah. So if you can show that this implies all the conjectures, all the extension of Wilf conjectures. Yeah, of course. Yeah. This is the more generalization. And yeah. What happens if you took, I don't know if this makes any sense, but you had sort of decomposed your linear algebraic groups into this unipotent and reductive. You took stuff the others. Yeah, so and this is also one of the future directions. So if we were able to define a similar theory for this, then we can successfully define the theory for all linear algebraic groups. So this would be a like a very general form of semigroup theory. Well, you have not done it. You've not done it yet, so this is still open. Yes, this is this. I have one more year in PhD, so maybe after PhD I will do something in this. Yeah. Any more questions?